I decided that one image of me wasn't enough, so now there's three different cameras to fill up all that black space. What we're going to be doing today is some review from Chapter 5, Unit 5 on stereochemistry, chirality, chiral centers, all of that sort of stuff. And this document is also posted up, just the blank document with the questions is up on Acorn. And these questions are all sort of harvested from old exams and midterms, just to give you more practice on this sort of question. First one asks, indicate any chiral centers with an asterisk and identify as R or S. So why don't we do that on this first one? We'll zoom it right up. First of all, anytime you get a question that asks you to identify chiral centers with an asterisk and indicate R or S, always the carbon's going to be sp3. Always there'll be dashed and hashed and wedged bonds, or else you can't determine R or S. So right away you want to zero in on carbons that have hashed and wedged bonds coming from them, which in this example would be that carbon right there. This, you can see, has 4 different groups attached. It has a CH3, it has a bromine, and it has the 2 carbons on either end going around the ring. So the first thing we need to do is determine the priority of all of the groups that are attached to the chiral center. And the first thing that we want to do is look at the bromine. The bromine has a higher atomic number than any of the 3 other carbons that are attached. So bromine is going to have first priority, number 1. Next, what we're looking at are 3 different carbons. And you can see there's a hydrogen here. This is a CH2. We draw in all of the atoms on those carbons that aren't shown because we're doing a bond line structure. And what we would like to do is maybe we'll just label these 3 carbons as A, B, and C. And we want to look at what is attached to these 3 carbons. Actually, I'm going to go back to pink. I'm going to go A, B, C. So carbon A, if you look at what's bonded to carbon A, coming away from the chiral center, it's a CH3, so it will have hydrogen, hydrogen, hydrogen. Carbon B, you can see carbon B has a double bond to another carbon. If it's a double bond, we list carbon twice, and then it has the hydrogen, which I drew in. Lastly, we have carbon C, and if you look at it, it has another carbon bonded to the next carbon down in the ring. So we list a carbon, plus it has the 2 hydrogens. So just keep in mind, when we list these 3 atoms that are attached to the group, to the carbon which is attached to the chiral center, we want to list those 3 things in descending order of priority. So carbons, then hydrogens. Now what we do is we compare everything in the first row, the first column, the first element of each set. And what we find is A has a hydrogen, B and C both have carbons. So B and C will have a higher rank than A. So A, what we can do is come over here and give it the lowest priority, which is 4. So now it's dealt with. Now we want to compare B and C to each other. B and C, if you look at the first element, they're tied. They both have carbons. But if you go to the second element, B has a carbon, C has a hydrogen. So that means B will outrank C. So the first rank was bromine, second rank will be B, third rank will be the carbon going down the left side of the ring. Next, what we want to do is orient the molecule so that the lowest priority group is facing backwards, facing towards the back. And that is the case already. The methyl, which is the lowest priority group, is pointing back. And then you look at the 3 remaining groups, 1, 2, 3, and look to see what the descending order of priority is. In this case, 1, 2, 3 goes around in a clockwise fashion. That means that this is going to have our stereochemistry. Great. Next question, B, same deal. Identify any chiral centers with an asterisk and identify with R or S. Now, this particular molecule, if you're going to look for chiral centers, basically what I said is you want to look for carbons that have a dashed and wedged bond, or one or the other coming from them. That would appear to indicate this carbon. However, if you look at this particular one, this is not a chiral center. It has, sure, a hydrogen going back. It has the cyclopropyl group sticking up to the top. But if you go around the ring this direction or this direction, it's exactly the same. Therefore, it's not a chiral center. Also, this molecule will have a mirror plane through there, and if a mirror plane intersects with a carbon, that carbon cannot possibly be a chiral center. So I guess our answer to this one is just no chiral center. Our last molecule is this one right here. Again, our eye may be drawn to this carbon here because of the wedged bond coming from it. We want to check and make sure that all of the 4 groups that are attached are different. We have an OH, we have a hydrogen, we have the acetylene group, or I guess you'd call that just an alkyne group, or we can call it an sp carbon. And then we have on the other side, which is a 1-methyl-ethyl group, which is also called isopropyl, which is an sp3 carbon. So yes, all 4 things that are attached to this carbon are different. So this is indeed a chiral center, and we can proceed from here. We want to identify priorities first. I'm going to change my priorities to green. First priority, we have oxygen, hydrogen, carbon, carbon. Oxygen will be top priority. Hydrogen will be bottom priority based just on atomic number. Oxygen has the highest atomic number out of oxygen, hydrogen, and carbon. Hydrogen has the lowest. The others are both carbons. So what we want to do then is we'll label them maybe A on the right, B on the left, and then compare A and B. So carbon A, coming away from the chiral center, is bonded to has 3 other bonds. That is a triple bond to the other carbon atom. So triple bond we just list as carbon, carbon, carbon. Next we have carbon B. Carbon B has a hydrogen there as well that's not drawn. It's got 2 bonds to carbon and a bond to hydrogen. So we now compare these one element at a time. First is carbon versus carbon, it's a tie. Second, carbon versus carbon, still a tie. Third, carbon versus hydrogen, A outranks B. A green pencil back, A gets number 2, B gets number 3. Orient the lowest priority group backwards, which is number 4, it's already in the right place. And 1, 2, and 3 go in a clockwise fashion from top to low, to high to low priority, which makes this one R as well. There's 2 R's. Question 2 says, what is the relationship between these 2 molecules? We love these questions. So, how do you handle a question like this? Well, let's redraw the first one. Okay. Does this have any chiral centers? Well, yes it does. It has one right here. What we would like to do is draw the molecule beside it in a similar orientation so we can compare them. You can see the one on the right here kind of looks upside down. So what I'm going to do is draw that one in blue, and what I'm going to do is just flip it around 180 degrees so that it's oriented with the bromine up, just like the molecule that's already there. So if we flip that around, that's going to have the bromine up top. The double bond, though, if you notice, if we flipped it around 180, the double bond is going to end up on the opposite side of the molecule, like you see here. Now these two appear to be mirror images of one another, don't they? They are indeed mirror images. They're also not superimposable. If you slid the structure, I wonder if I can actually do that. No, I'm wasting time. Maybe? Yeah. Anyway, in this structure you can see that they're mirror images of each other. They both have chiral centers. They're not superimposable because if you slide one on top of the other, everything lines up except the position of the double bond. So these to me look like enantiomers, chiral molecules whose mirror images are not superimposable. Another way you could have managed this particular question is noted that they look very similar except they both have chiral centers. You could identify the chirality of each one. So if you look at the structure we have here on the right, and you were to label this as R or S, this one becomes R and this one becomes S. So if you have a pair of similar molecules that are an RS pair, they will be enantiomers. 3. Identify the stereochemistry of the chiral centers in the following compound. There's a number of ways to handle a question like this. This is a Fisher projection. You could draw it out in sort of a normal ball and stick with tetrahedrals, but I'll find an easier way to do this is just to use the template that we have here, just use the Fisher projection itself, and start by identifying the priorities. Now Fisher projections, whenever you have an intersection point right here, those intersection points are meant to be chiral centers. So this has 2 chiral centers. So what I'm going to do first of all is focus in on atom number 2. I'm going to redraw it a little bit bigger. CH3H, and then this becomes H and H2. I'm just shrinking this down a little bit. OOH. And so what we will have is we have 4 different things attached to this chiral center on carbon 2, and we want to assign priorities to each of those groups. First of all, hydrogen gets the lowest priority right away, and then we're comparing carbon with carbon with carbon. So let's call them A, B, C. A, the carbon on A has a double bond to oxygen and then a single bond to oxygen, so it gets OOO. Next, for B, you can see B is hydrogen, hydrogen, hydrogen. And finally, for C, we have it bonded to a nitrogen, a carbon, and a hydrogen, and we want to draw these in order from highest to lowest priority. There's nitrogen, carbon, hydrogen. Now we compare the first element in each set. The highest of this bunch is oxygen. So right away we can give the top carbon first priority. The next best priority there is nitrogen. So 2 comes down here. And then the lowest is the hydrogen, which gives 3 the priority over there. Now, what this Fisher projection actually means is that anything that's in a horizontal position is coming out towards you. It's not going towards the back. And anything that's vertical is going back away from you. So our lowest priority group is not pointing back. Our lowest priority group is pointing forwards, which is the hydrogen. So what we can do is assign the stereochemistry based on the other 3, ignore the lowest one, and then whatever we get as a result, flip the result because we have the hydrogen pointing in the wrong direction. So let's do that. 1, 2, 3 goes around in that direction. That's counterclockwise. Counterclockwise is S, but the hydrogen is not pointing back, it's pointing in the front, so it's not going to be S, it's going to be R. So So right away we can say that this stereocenter here is going to be R, or 2R, indicate carbon 2 is the one that's R. So right away we can look at our answers here. B is out, D is out. Meso would be if there's a mirror plane inside the molecule, which there is not, so it's out. So it's down to either 3S or 3R. So now we've got to do this all over again, except we have to look at atom 3. So I'm going to just go to the left here and look at atom 3, where we have a hydrogen, an NH2, a CH3, and then this is a carbon 2 with a methyl and all the other stuff it's got on it over there. So this is the one we're looking at. We want to assign priorities. Lowest priority again goes to the hydrogen. Highest priority will go to the nitrogen because it has a higher atomic number than carbon. And now we're comparing the top carbon and the bottom carbon right here. Bottom carbon is bonded to hydrogen, hydrogen, hydrogen. The other carbon is bonded to carbon, carbon, hydrogen. So the winner is going to be this one. This gets priority 2. This gets priority 3. We ignore the lowest priority group for now, and we go 1, 2, 3 in that order. That is also counterclockwise. So this would be S. However, remember that the hydrogen is pointing front because it's in a horizontal position, not back. So we flip whatever our answer was, and we now have R. So 3 is R as well. That means the correct answer here is C, 2R, 3R. A lot going on here, but both stereocenters here are R. 4. Which of the following structures is optically inactive? So for optically inactive, this means the molecule must be achiral. So for it to be achiral, notice that every single one of these has chiral centers. The only way you can have chiral centers and not be a chiral molecule or be optically inactive is for there to be a mirror plane within the molecule, which would make this a meso compound. So looking right away, E, you can see, has only a single chiral center. If it has a single chiral center, it has to be chiral and it has to be optically active. So let's get rid of that. D, let's look for a mirror plane. I mean, the best shot at a mirror plane here would be down here, but you can see that on one side there's an ethyl, on one side there's a methyl. So there's no mirror plane in this molecule. So D is not an option. Similarly, C doesn't have a mirror plane either. Looks like it might, but it's got a double bond on one side and not the other. No mirror plane for that one. Now we're down to A and B, and A and B, the way they're drawn, neither one has a mirror plane, but keep in mind that these are single bonds that can freely rotate. So what we want to do to check to see if there's a mirror plane in either of these molecules is redraw them, but in the eclipsed form, where all the bonds are eclipsed. So we're going to do a rotation around the bond I indicated here of 180 degrees. So if we leave the left-hand structure all by itself, the left-hand half of the molecule, A will look like this. So we left the left-hand part, and we flip the other one around, so the methyl is down, and the OH, if it's pointing forwards, if we spin it around 180 degrees, will be going back like that. So that one is A. B, we can do the same thing. If you flip it around, the OH comes forward. So I would, if I were you, practice rotating single bonds around and redrawing what the product will look like. This one is B, because this is a useful skill. When you start out, you might find it helpful to build the structures using a model kit, like this one I have here. And if you use the model kit, maybe it'll make it more clear what's actually going on in these cases. Now, if you look at these newly drawn structures, we could say that B has a mirror plane that draws through like that. which maps the left side and the right side of the molecule. So B is meso, and meso structures are optically inactive, which is B. Draw examples of each of the following. This is another one of my favorite kinds of questions. We want to draw a pair of enantiomers, so basically we just want to draw any chiral molecule we can think of. Take a simple one like OH. It's got a chiral center. What's important is you have 4 different groups on there, and the enantiomer will look like its mirror image. And there's different ways you can draw it. You can draw it like this. Very clearly has a mirror image there. Another way you could have drawn it is just redraw it the same way you did the first time, except change the orientation of the wedged bond to a hash bond. These are the same thing. A meso compound, well, if you want to go back to one and like steal this one, you could, but that's cheating. Let's get a new meso compound. Meso compound is one that has 2 or more chiral centers and a mirror plane in the molecule somewhere. Let's go with this one. This is just a random one. You can see there's a mirror plane through the molecule like that. There's 2 chiral centers here and here, but they're mirror images of one another. Next, a pair of diastereomers. So a pair of diastereomers, where's the bottom of my page? Anyway, I don't think that matters. Pair of diastereomers, these are stereoisomers, but not enantiomers. They can't be chiral mirror images of each other. Diastereomers usually are related by a cis-trans relationship. So here's an example. You can have, I always go to that example. I'm going to give you a new one. You could have CH3 OH OH. So you can see that these are the same structure, except the left one is cis and the right one is trans. Another example, if you want to get fancy, you could draw out cyclohexane and draw something like CH3Cl and CH3Cl. This one is cis. It's not the most stable conformation of cis, but that's cis. This one is trans. By the way, when we get to look at alkenes more in depth, alkenes come in cis and trans as well. And these are also diastereomers. Back to blue. For the following molecules, indicate which carbon is the chiral center by marking it with an asterisk and determine if R or S. Good thing about these questions too, if you have no idea what to do, it's 50-50. But we're not going to rely on that, are we? First one. That's the chiral center with the wedged bond coming off of it. Let's add in atoms that are not drawn. Hydrogen in the back. Priorities. Bottom priority is the hydrogen. Top priority is the chlorine, based on atomic number. Next, we have 2 carbons in the chain. We have this carbon, which is a carbon bonded to 3 hydrogens, coming away from the chiral center. This one is a carbon bonded to a carbon, a hydrogen, and a hydrogen. So that means the left one is higher priority because the first element, which is carbon, beats the first element, which is hydrogen. Lowest priority group is back already. I'm going to change to green. More colors. So 1, 2, 3 goes around in a counterclockwise fashion, meaning this one is S. Next structure, chiral center is there. Let's draw in our missing atom. which is a hydrogen. This is a tetrahedral, so you'll always have a dash and wedge bond and then two bonds in plane. So this particular one, we can go lowest priority is the hydrogen, highest priority is the OH, and then we have carbon versus carbon. So this one might get a little long. We're comparing this carbon and this carbon initially. So if you look at that one, that carbon is bonded to a carbon down the chain, plus two hydrogens. This carbon is bonded to a carbon down the chain, and two hydrogens. So they're perfectly tied. So then what we must do is step another carbon down the chain. So we want to kind of head down the carbon chain this way, and now we want to compare this carbon with this carbon. And we keep going until there's a difference. So now this one has a double bond. So we go carbon, carbon, hydrogen. And then the bottom carbon is a single carbon, and it's a CH2, so it's CHH. This one is higher priority, so the priority will go 2 on this side, 3 on this side. Now, if you look at 1, 2, 3 going in decreasing order of priority, 1, 2, 3 goes around that way, which would be S. However, the hydrogen, the lowest priority group, is not pointing to the back. We could either redraw it, flip the molecule, or we can realize that if the hydrogen isn't pointing back, we just swap whatever we thought we had before. So that means this one's R. This molecule is an amino acid. This looks like serine. We have a chiral center here. We're going to draw in the other bond, which is a bond to hydrogen. Priorities, lowest goes to the hydrogen. It's pointing back, so that's good. Next we have a nitrogen and two carbons. The nitrogen will get top priority because it has the higher atomic number. Now we got to compare this carbon and this carbon. That carbon is bonded to oxygen, oxygen, oxygen. You list oxygen twice for the double bond. The other carbon is bonded to oxygen, hydrogen, hydrogen. So first element, they tie. Second element, the higher priority group goes down to the bottom. The lower priority group goes up to the top. 1, 2, 3 goes around in this order, which is clockwise, which is R. And we're going to keep R because our hydrogen is pointing back. This one has two sites with dashed and wedge bonds. There's one here, but that one is not a chiral center because it has two groups that are the same, two methyls. This, however, is a chiral center, and we can, maybe I should use black. We're going to draw a wedged bond here. With our hydrogen, we're going to put our missing bond in. And priority time. Highest priority is fluorine, lowest priority is hydrogen. We're comparing carbon and carbon. So if you compare carbon A, which has carbon, hydrogen, hydrogen, with carbon B, which has carbon, hydrogen, hydrogen, they tie. So you step down the chain to compare that carbon and that carbon. This is bonded to carbon, which is continuing around the chain, hydrogen, hydrogen. And this one is carbon, carbon, carbon. And so B wins, B gets number 2, A gets number 3. 1, 2, 3 goes around this way, which would be S. But keep in mind, again, the hydrogen is pointing in the front. It's not pointing in the back. If you flipped it, that would reverse it from S to R. Last example over here on the right. Our chiral center is here. We should draw in our hydrogen that's pointing back and give hydrogen the lowest priority like always. And now we're comparing three carbons with each other. Carbon, carbon, carbon. We'll call A, B, and C. Carbon A is bonded to hydrogen, hydrogen, hydrogen. Carbon B is parentheses, carbon, carbon, carbon for the triple bond, and carbon C has a hydrogen, carbon, carbon, hydrogen. All right, highest priority of those three would be B. Second highest priority is C. Lowest priority is A, which is 3. So now we have 1, 2, 3. Goes around clockwise, which is R. There we go. For the following pairs of whatever molecules, indicate if they are the same enantiomers, diastereomers, or constitutional isomers in the spaces provided. Okay, let's look at this set right here. First of all, we have no chiral centers. There's a mirror plane that goes through the molecule in both cases. No atoms have 4 different groups, so enantiomers is off the table. You can see that the two methyl groups in the first one are coming towards us. One's coming away and one's coming towards us in the second one. This to me looks like a cis-trans pair. Cis-trans pairs are diastereomers. Next, we have two molecules, each of which has a chiral center. You can try to rotate the molecules around and see if they line up with each other, or you can just identify R or S. So the left structure has a hydrogen. Fluorine gets number 1, ethyl 2, methyl 3, hydrogen 4. That means priority decreases going that way, which means that's R. We can do the same thing over here. Notice there's a hydrogen in the front. Priority goes this way, which is R, but the hydrogen is facing the wrong way, so it means it's actually S. These are both 2-fluorobutane, but one is R and one is S. This means these are enantiomers. Chiral molecules that are mirror images of each other. Next, we have a very similar situation. We have a chiral center on a molecule that you could identify as R or S. You can tell maybe without even identifying R or S that these two will be mirror images of each other. And as non-superimposable mirror images, these are enantiomers as well. Next, we have two Fischer projection versions of a molecule. In this one, both fluorines are together on one side, and this one, they're opposite sides. This is sort of like a cis-trans pair. We actually have names for these. We don't use cis and trans on Fischer projections. We didn't cover it in class, but they're called threo and erythro. But either way, they behave like cis-trans pairs, and these are diastereomers. Next, we have two molecules with the double bond in different positions. The connectivity of atoms in this case is fundamentally different, right? This one has a CH3, this one has a CH2. So these ones would be constitutional isomers. Using the following. Convert the following compounds to the Fischer projections using the templates provided. And the vertical chains are the vertical lines are supposed to be the carbon chains. So what we need to do to make something into a Fischer projection is, first of all, we're going to rotate the bond so that the groups are all eclipsed. Because this is going to be carbons 3 and 4. That's going to be 3 and 4. The cross points there, the intersection in the Fischer projection, are the chiral centers. So what I'm going to do is rotate that around 180. I'm going to redraw it up above, and I'm not going to change anything on the left side, I'm just going to change the right side. And if you flip that around, you get something that looks like this. Now everything's eclipsed. We have hydrogens here, and we want to view this molecule as if our eye was here. We want to view it as if the carbons are going back and are vertical up and down. So that means this will be our ethyl chains. So if you label these 1, 2, 3, 4, 5, 6, this becomes 1, 2, 3, 4, 5, 6. Looking at carbon 3, if you were looking from that vantage point, where that's your face, you have no forehead, but you know what I mean. Then it would appear as if the OH would be on your left, and the hydrogen would be on your right. And looking at the next carbon, carbon 4, similarly, the OH would be on your left, and the hydrogen would be on your right. So that's what that would look like. Does it also want, no, that's it. Doesn't want you to determine R or S. You could do it, but we did one like that before. So for this next one, we want to redraw it with everything eclipsed. I'm going to leave the right side the same. I'm going to rotate this way around 180. If you do that, the methyl will be eclipsed with the other methyl. The Br comes down this way. Hydrogen here, and what we want to do is have our eyeball here. Looking at the molecule like that, so that the carbon chain is vertical to you, up and down, and going back. So these two CH3s would be here and here. We don't have to write the CH3 in, because just the ending of the line suggests a CH3, but you can do it if you like. On the top carbon, look at carbon 2, 1, 2, 3, 4. Carbon 2 has a bromine that would look like it's going to the left from that vantage point, and a hydrogen to the right. And carbon 3 would look like it has a fluorine to the left and a hydrogen to the right. You could have drawn it the other way around. For example, if you were not laying in that direction, but instead were laying in this direction. This is a really ugly looking person. But you can draw it as well from that, which would basically look the same except flipped 180 degrees. Another similar one, convert the following molecules into Fischer projections using the templates. A, we just want to, again, reflip. We want to rotate that around 180. That would bring the methyl down. The chlorine would flip up and come like this. Draw our hydrogens. Now we have it drawn out so that everything's eclipsed. If we go 1, 2, 3, 4, 1, 2, 3, 4. Carbon 1 and 4 are methyls. We can leave them be. Carbon 2, remember we want to view it from a vantage where the carbon groups are vertical and going back away from the eye. That would mean looking from that angle, that's your nose. The OH is on the left, hydrogen on the right, Cl is on the left, hydrogen is on the right. Okay, molecule B, let's rotate this around a little bit too. First I'd like to, no, we're good. We're going to leave the top one. And we're going to rotate the central bond around 180. So it puts the methyl over here, and that would put a bromine out. So when you rotate it around, anything that's wedged becomes hashed, and vice versa. draw our hydrogens, draw our I. Looking at the molecule, that would look like Cl is on the right, and it would look like bromine is on the left. And this is correct. Consider the following two molecules. We got more of these. What is the relationship between them? Note the two groups here, the OH and the methyl, are cis and trans. Diastereomers. How about these two molecules? Look what would happen if you rotated that one around 180. It would look identical to the one on the left. These two are the same molecule. Next, notice these are both cis-dimethylcyclopentene, but this is 1,2 substituted, and this is 1,3 disubstituted. So the methyls are attached in different places, so they're not diastereomers, they're not enantiomers, they are constitutional isomers. Next, we have, in this case, this is a cis, because both groups on the double bond are on the same side. This one is trans. We didn't quite get to alkene cis-trans yet, but we will. For when we do, those are diastereomers. How about this molecule? This, if you look at the longest carbon chain, has 6 carbons, so these are both hexanes. They both have 3 methyls. This one would have 1, 2, 3 trimethyl. This one would have 1, 2, 5. No, that's not 1, 2, 3. Delete, delete, delete. This is 2, 3, 4 trimethyl. This would be 2, 3, 5 trimethyl. So the connectivity is different. The methyls are attached on different positions. So these are constitutional isomers. Question 10. What is the enantiomeric excess percent EE of a mixture that is 75% R, 2-bromobutane, 25% S, 2-bromobutane? Pray you get a question like this, because these are dead easy. Percent EE is just the percent major minus the percent minor, which is 75% minus 25% equals 50%, which is C. Which of the following molecules is chiral? A is not, because A has a mirror plane through it. That makes it meso. D has no chiral centers. Notice it has a mirror plane through it as well. It's not meso though. You need to have chiral centers to be meso. B though, it doesn't have a mirror plane. B has 2 chiral centers here and here, but they're not related to each other by a mirror plane. So B is chiral. C is not, because C, if you rotate the bonds to make them eclipsed, they'll look like this, which has a mirror plane. This one's meso. And this one also will have a mirror plane through there. We could just rotate 2 bonds like this. Has a mirror plane. This one's also meso. So B is the correct answer. Question 12 says, which of the following 5 choices best describes the stereochemistry of the molecule shown below? Is this the exact same one we did before? No, it isn't. Not exactly, because this is an aldehyde at the end. Anyway, same procedure. Let's zoom in on carbon 2 to begin with. Hydrogen, OH. We have in this one HO, methyl hydrogen, and OH. Rank priorities. Bottom goes to the hydrogen, top goes to the oxygen, and now we're comparing a carbon with a carbon. Top carbon is bonded to oxygen, oxygen, hydrogen. Double bond oxygen means we label it twice, we list it twice. Bottom one does have an oxygen, but then it has a methyl carbon and a hydrogen as well. So comparing the first elements, they tie. Second elements, the higher priority group is the oxygen one, which is up here, and then that means this group is priority 3. Ignoring the low priority group, 1, 2, 3 goes around that way, which would be S, but the hydrogen is in a horizontal position, meaning it's coming forward, so we flip whatever we got. It's not a dollar sign. It's not S. This one is R, so it's 2R. So let's get rid of these 3 possibilities. And next, we're going to zoom in on carbon 3. Carbon 3 has HO, CH3, hydrogen, and then of course carbon 2, which is an OH, a hydrogen, and the aldehyde group. So, priority time again for carbon 3. Top goes to oxygen, bottom goes to hydrogen. Next, we're comparing a methyl and a methyl. Top one has oxygen, a carbon, and a hydrogen. The bottom one has hydrogen, hydrogen, hydrogen. Higher priority is the top one. Next lowest priority is the methyl. 1, 2, 3 goes around clockwise, which normally is R. But the hydrogen is in a horizontal position once again. So the hydrogen, because it's horizontal, we need to flip whatever stereochemical designation we got. So it's actually S. So this one becomes 2R3S, which is B. That's it. We're all done.